Now, of course, your model was not automated using the TTP at the time. You know, could have turned it into a self-driving battleship with 256 locations in RAM. Yes, we can do it. No, it's a shell, right? You know, so when the outer shell becomes completely bombed out, it opens up and there's a smaller ship that comes out. And it keeps doing that until there's one last torpedo that comes out. And then it shoots out a little message in a bottle that says, screw you. And that will be the end of it. Yep. Okay, so I think OBS has been recording. Yep, okay, and the voice is up. Good. All right, so what we'll be talking about today is more stack-based operations. And to be more specific, we're going to talk about a few sample programs. I may not be using the same sample program like in my Monday, Wednesday class. So you might want to check out their lecture as well if you have time and you think, okay, a little bit more exposure is not going to hurt. And I need to turn off OBS just because I have to change the screen resolution because I can only see what OBS is seeing right now, but you guys are seeing a lot more because of the difference between the resolution of my monitor versus the projection screen. So I'm going to have to change resolution, which is going to mess up OBS. So, or maybe not, because it's actually changing to a lower resolution that is already being recorded. We'll see. And OBS is still okay, so I think it's still okay. All right, cool. And we'll just say close right here. All right, so what we'll do is we'll begin with a program in C and C++, C/C++. Most of the programs that I write are pure C programs, which means it will compile with a C++ compiler, but it's not using any features of C++. There's no object-oriented programming. So here we go. We'll go ahead and write our first program. I think in this class we talked about how to return a value already. Yes? No? Okay. Register A. Okay, so somebody remember that. Okay. So register A is the designated register to return a value. So this is an agreement, okay? All that is an agreement. There's nothing in the processor itself that says, oh, register A is special, it is the return value. There's nothing like that. It is an agreement between the caller and the callee, the subroutine that's being called. And that's what the compiler does. The compiler is basically compiling code to make sure that whatever code is doing the calling would follow the same rules that the subroutine being called is going to follow, so that they both agree that register A is the return value. So the subroutine being called will put a value into register A, and then the subroutine who's calling, the caller, is going to look at register A when the subroutine called is finished. So that's how things work out between the caller and the callee. So what we'll do is, in this class, I'm going to look at a subroutine like this, okay? uint8 underscore t is really just saying unsigned char, okay? But I'm using this particular notation because I really want you guys to start to use these particular types so that you are aware of the width of your integers, so that when you write any code that needs to be recompiled on different platforms, it won't matter whether it's a 16-bit, 32-bit, or 32 or 64-bit platform. Your code will still compile. It will still work the same way. And this particular subroutine, I'll just call it F. You are passing a pointer to it. So uint8 underscore t star ptr. And what it's returning is really simple, okay? It's just returning whatever ptr points to. In other words, F is just dereferencing, okay? But I want to look at this function, look at the caller, look at how this function is implemented. So this way we can actually start to look into how do we push parameters on the stack? How do we push the address of something on the stack? How do we get to a parameter? How do we dereference a parameter? And how do we return a value? So this example program will illustrate all of those concepts. Okay, so now we need to specify main, which is the only caller. So we'll also look into how to deal with local variables. So main is the entry point of any C program. And in here, we have uint8 underscore t. And let's say we have a local variable x. Well, let's do it this way. X equals to, we initialize x first to, let's say, 6. And then on the next line, I'm going to do something like this. F of the address of x plus, okay, I'm not going to make it tricky. I was about to say plus x, but that becomes kind of implementation dependent or compiler dependent. Some compiler, if they parse x first, then the second x is going to be frozen in time and not affected by the operation itself. So I'm not going to do something tricky like that. This is all I'm going to do. So are there any questions about the C program itself? Questions? Now, if you do have any questions about the concept involved in this program, you can just finish the whole thing, because as it is, it's not going to compile, but with the pound include, it will compile. So when this program compiles, you can track down line by line using a debugger and find out what is parameter PTR by the time you get into the subroutine, and also eventually how X is going to be updated on those two lines. Is that okay? So that's one way for you guys to kind of find out what the C code is going to do and understand the concept in terms of C. But the focus of this class is the assembly code, so that's what we're going to do. I'm going to open up another mousepad. Okay, where is that? I have too many mousepads open. I think maybe this one. Yep, okay, there we go. All right, so the first thing I need to do is to make sure that we understand there's only one entry point in your TTP program. Your TTP ASM program only has one entry point, which is location 0. So you don't really have a choice but to say main has to be the first thing. Okay? So main being the first thing we need to do here is to, okay, before we even do anything with the local variable, we have to initialize the stack pointer. Technically speaking, you do not need to, because the only way that we want to initialize the stack pointer is either a sub DD or a LDI D0. Both will do the same thing, because all we want is register D to start with a value of 0. Okay, can I answer your questions? No. Can I answer your question? I really mean it. I'm not. Okay, all right. Okay, so yeah. Well, that is a good question, but I think you can answer that question. So what is sub? What does it stand for? The mnemonic of sub is representing what? Subtract. Okay, what is it subtracting from what? And yep, so that's why D is initialized to 0. So there are two differences between these two instructions. One is kind of minor, the other one is kind of significant. The minor one is the first instruction only takes 1 byte in memory. It is a shorter instruction. Okay? The second one takes 2 bytes because anything that ends with an I as a mnemonic is an immediate operand, and the immediate operand itself takes up 1 byte after the opcode. Is that okay? So that's kind of a minor difference. Okay, we chew up 1 more byte in memory. The second difference is kind of significant because subdd is, after all, an actual subtraction instruction, so it will overwrite all the flags. Okay, the carry flag is going to be a 0 because subtracting a value from itself should not trigger a borrow. Z should be a 1 because the result is a 0. CZ sign should be a 0 because the value of 0 has the sign bit being a 0. Overflow should be a 0 because subtracting a value from itself should not trigger overflow. And then the L flag should also be a 0 because we have sign itself being a 0, we have overflow being a 0, 0 exclusive or with 0 is 0. So the only flag that is going to be a 1 is going to be the Z flag. All other flags should be zeros. Okay? But it will change. It will update all the flags. So if you are doing this, but you really want to keep track of the result of an earlier compare, subtract DD is going to destroy that. But LDI D0 is not going to do it because it's not going to touch the ALU at all. So that's kind of the difference between these two instructions. But I'm going to go for the one that is shorter because at this point I don't really need to preserve the flags register because there's no compare before this. So what this instruction is doing, I'm going to comment the program as I type to explain. This is to initialize the stack pointer. So why would I initialize the stack pointer to 0? Well, that's because the intention is to initialize the stack pointer to 1 byte past the end of the chunk of memory that I'm allocating to the stack. The stack basically starts with whatever is at the end of the program, all the way to the end of the entire memory module, the RAM component, which is location 255. So I really want to initialize the stack pointer to 256. But that's a 9-bit number. It's 1 followed by 8 zeros as a binary number, which cannot be stored. When I store that 9-bit number into an 8-bit number, it becomes just 0. That is the reason why I initialized the stack pointer to quote-unquote 0, because I really intend it to be 256, but 256 stored as an 8-bit number is just 0. Is that OK? Yep.
So like the very first decrement's an intentional overflow, right? Because you're overflowing from 0 back to 255.
It's not really overflow in the sense of the overflow flag. It is really just, it's not really an overflow. It is really just crossing that 0 boundary in a negative direction. That's the best way to describe it.
Is that not an integer overflow?
Huh? It is not an overflow. Well, in this class, the word overflow is specifically applicable to signed values. And this is not an actual overflow because 0 minus 1, even if you look at 0 as a signed number and 1 as a signed number, that does not trigger an overflow because the result is -1. So you have positive minus positive, non-negative minus non-negative getting a negative, and that is not by definition an overflow situation. So I would be very careful to use the word overflow because it has a very specific meaning as a flag. I know what you're referring to, that we are going under, we are wrapping around. So the best way to describe it is we're wrapping around more so than it is underflowing or overflowing. Okay, so the second line is decrement D. We are allocating space for the local variable x. Because the stack starts at high location, every time you allocate and want to store something, you are decrementing the stack pointer. Okay, it is counterintuitive, but it does work out really well that way. Okay, now that I have reserved the space, I can now store a value. Okay, because you always want to reserve the space and then you store the value and not the other way around. So you always want to adjust the stack pointer and then you store something to the location pointed to by the stack pointer. So right now I'm going to store the 6, which is kind of cumbersome because I have to load another register with a value of 6, and then we store register A to where D is pointing to. So the effective these two lines effectively implements x equals 6. Are we still doing OK so far? We allocate the space, but it is uninitialized. So in order to make sure that that local variable has a value of 6, I have to load immediate 6 into register A, and then we store register A to wherever D is pointing to, because D is currently pointing to local variable x. Are we still doing OK so far? Okay. Yep.
So we're basically saying that there's like an imaginary x in that spot?
OK, let's see if we can do it this way. I'm going to open a new spreadsheet, basically to use it to display what is on the stack right now. Okay. All right, so the last location is 255. So column A is basically just the addresses of each location. So we have 255, 254, 253, 252, 251, and I think that should be all we need for this particular sample program. So when D is 255, I store a 6 into it, and this is what we know as local variable x in the C code. In assembly code, it does not have a concept of local variables or types or stuff like that. So when we translate the code, we can only use comments to indicate of what it is, but it doesn't really, there's no actual native concept corresponding to it.
So it's basically like as close as we can get.
Yes. Yep. All right, so after this, in the C code, we have to perform the next line. So what do you think is the first thing we have to do when we have x equals to f of ampersand x plus 1? Now, this is a trick question, because when we read code, we read from left to right. And as a sorry?
Start from right to left.
Yes, in an assignment statement, what you need to do is to evaluate the right-hand side first. The right-hand side gives you a value, and then you store it into the left-hand side. So before you evaluate the right-hand side, the left-hand side really doesn't matter. You don't have a value to store yet until you have evaluated the right-hand side. So our focus is going to be on the right-hand side. Okay? So on the right-hand side, we have f of ampersand x plus 1. The plus 1 is pretty easy to deal with. Okay? So I'm not worrying about that. So what we really need to do first is to call function f with the argument of the address of x. Is that okay? All right. So now I'm just going to comment here and say that the following code computes the address of x, which is trivial. Do we have to do any computation to get the address of x? We don't. Now, but how do you push it on the stack? Okay, so I'm going to comment right here. D is the address of x. Does that make sense? Because we are not going to move on until this statement is clear, because the rest kind of depends on this statement. So are we clear why register D currently is pointing to local variable x? After all, we just stored a 6 into it, right? So D has to be the address of x. But we have to push that value on the stack, which becomes kind of difficult, right? Because what two operations do we need to push something on the stack in terms of mnemonics? Decrement to allocate, st to actually do the store. But the moment you decrement D, you lost the value that you need to store.
Couldn't you just do like a copy register before you even do any of that, and then copy D before you decrement?
Yep. And same thing? Okay, very good. So we got two people coming up with the same answer. Very good. So CPR is a really useful instruction because in this case, we are basically saying, okay, let's also make C equal to the address of x. So I'm intentionally using double equal to state that C is the address of x, okay, after this operation. It is not an assignment operation. It is an assertion that register C is the address of x. So now that C is the address of x, I can now freely modify D, which its main job is the stack pointer. It is not supposed to be used as, oh, I want to point to this variable, I want to point to that variable. It is the stack pointer. So as a stack pointer, I'm going to decrement it to allocate for a space for argument to function f. Okay. So once I allocate a byte, now I can use it. Okay, you always allocate first before you utilize it. So we utilize it by storing into whatever D points to the value of C. So this is the same thing as pushing ampersand x on stack. We're passing the argument. Okay, we're computing the value, we're passing it on the stack. Now that we have set up the parameter, it is time to push the return address. So we have to do LDIA with main return from f. Okay, long label name, but it kind of self-explains. And then main return from f is down here. Now, because it's streaming, there's no need to really copy down everything, but you might want to write down, concepts that are important to you, and also the timestamp of, where this is in the video, because that allows you to index back into the video quickly instead of having to watch from the beginning to the end. Okay, so now that we have this in A, the next thing is to do the same thing, decrement D, but I'm going to comment and basically indicate what are we allocating for this time. We're now allocating for the return address on the stack. And then we store A on the stack, so we basically push the return address. Now that we have the argument pushed and then we have the return address pushed, it's time to say, hey, subroutine F, go do your thing. That is a JMPI instruction. Just go to the label F, which we'll define later. So we are now continuing execution in the subroutine F. When subroutine F is done, there's one thing that the caller has to do. The caller has to deallocate the byte that is used by the argument. Because the subroutine is done already, why do you still need that byte storing the address of X on the stack? We don't, okay? It's already utilized. So it is the caller's responsibility to deallocate the arguments on the stack after a call to a subroutine. So we do it with an increment D to deallocate argument to function F, because that is of no use at this point. You might look at this code and go like, what about that return address? Because we push the argument and then we push the return address. Shouldn't we pop or deallocate the return address first and then deallocate the argument? And why not?
Because the call function is supposed to do that as an instance, right?
Exactly, because the called function is supposed to utilize and deallocate the return address. The caller does not need to worry about the return address itself. Yep.
So like any values we use in the stack in F, those will still be on the stack, just on the other side of the pointer still, right? Because we're not overwriting them.
That's a very good question. We'll get to that. In fact, as soon as I'm done with this code, we'll talk about that. So can you remind me? Okay.
Maybe.
Okay. So let me rephrase or repeat that so that it's recorded. The question was, everything that is on the other side of the stack pointer is still there on the stack. It's just that the bookmark has moved, but the pages or the content of the pages should still be there. That is a tricky question to ask. With the toy processor, yes. Okay, you're guaranteed that the content is not going to change, whether it is above or below the stack pointer, unless your code has explicit code to change that. In an actual processor, that is not necessarily the case, okay, because of interrupts. So we'll talk about that, after we're done with this program. All right, so getting back to this program, we are now done with the function call to F. Can someone tell me again what is the purpose of calling function F? It is inside a larger, bigger construct. What construct is that? It's in main, but to be more specific, what is it doing? What am I going to do with the function call to F? Whatever it returns is important because I need to do something with it, right? So there are two things I need to do after this, that relates to the function call. What is the first thing I need to do? I'm done with this part, but the right-hand side is not just the function call to F, is it? We have to add one first, right? So the return value is in register A already, and that is a convention. So now I just need to add one more to A. So now A has the return back to here before the increment D. After the increment D, it points back to local variable X. So, which is really convenient because now I just have to say, Okay, where's my pointer? Oh, okay. So at this point, I just have to say store to whatever D is pointing to, which is my local variable x a, which is not just the return value coming back from f, it is one more than that, okay, because we did an increment of that. So this statement, or this particular mnemonic, is actually doing x equals 2, and this time I'm using one single equal sign because it is the actual assignment operation in this context. Is that okay? Cool. So you can see that in the C code, there's nothing really after this. There's a return 0. But in assembly code, in a TTP context, there's nothing for main to return to. Okay, you cannot get back to the IDE. You're not getting back to a command line interface. There's nothing to get back to. So the only thing you can do is a halt instruction. But before I get to the halt instruction, there's one more thing I want to do. Because at the end of every subroutine, you really need to deallocate all of the local variables that you put onto the stack. So I'm going to increment D one more time, and this time to deallocate local variable x from main. Then I'm ready to say we're done with this particular subroutine. And by the way, by the time I get to the halt instruction, what do you think should be the value of D, register D? 0. Yes, it should go all the way back to 0. In other words, the stack pointer should be balanced. Okay? When you look at the stack pointer at the beginning of a subroutine and you look at the stack pointer at the end of the subroutine, they should be the same. Cool. This is the main or the caller. Yep.
So let's say you make a variable. You use a register that you haven't used in like a previous subroutine. When you want to go back to main, how do you reset one that you didn't use in others? Like, so let's say I have register B, and I assign it to something in D. So like, let's say D is at 254, and I assign B to that. When I get out of that subroutine, what do I do with B?
Okay, so the convention is the register D should always be the stack pointer. Register A can be a return value if there's a return value from the subroutine, but register B and C are not supposed to be preserved by the subroutine. So if the caller needs to retain the value of, say, register B, across calling a subroutine, the caller itself is responsible to put it somewhere else and then restore the value of that register when it needs it back.
Okay, so I don't need to reset because we're not assuming it's like a goal.
The subroutine is not responsible to save and restore register B or C. The caller is responsible.
Okay.
Yep. Mm-hmm.
Is there a reason why we don't? I might be missing something, but there. So let's say that in F,
Mm-hmm.
we pop off we deallocate the pointer, or the.
But you cannot. You're not supposed to. Because from the perspective of the caller, the stack pointer should be pointing to the argument when the subroutine returns. That's the agreement. That is the convention. So the subroutine can only pop the return address, but not the argument.
Why is that? I don't understand.
Because that's the convention, so to speak.
Is there any like technical reason? Like
Yes, there are technical reasons because in most architectures, the return operation is done by a single instruction. And that one single instruction would first copy the value pointed to by the stack pointer to the program counter, and then it's going to increase the stack pointer by 1. And it's atomic. You cannot separate and only say, I only want this and not the other operation. So, and because of that, the assumption is by the time the subroutine gets back to the caller, the return address is deallocated, but only that. The arguments will still be on the stack.
I guess I don't understand why that's the convention.
Because the return instruction as a single instruction is doing that because the return address serves no purpose on the stack at that point. And as a result, it is deallocated. Now, how come the arguments are not deallocated? Because you can argue and say that the arguments are of no purpose at that point. But the subroutine doesn't know how many arguments there are on the stack.
That makes sense.
Now, and then, yeah, go ahead.
I'm just trying to figure out. Okay, so after we actually go to line numbers, after we push the return address into D, right before main return.
You mean here?
We jump to F.
Mm-hmm.
Where is F?
I have not written F yet.
Okay.
Yep. Okay, one more question? Yep.
I think continuing from the question about reallocating memory from
Mm-hmm.
the subroutine.
Yep.
When you say that it's the convention,
Mm-hmm.
who decides that? Is that just the industry standard, or is that?
It is more or less an industry standard, but for the most part, if we can deallocate, because we know there's no use of something, we will deallocate. The problem of the parameter or the arguments is we do not know how many arguments are on the stack. Now you might say, but we always know what type and the number of arguments. Are you guys forgetting the ... Because in C and C++, you can pass a variable number of arguments to a subroutine. That is the problem. We do not know how many arguments there are on the stack. And as a result, the convention is, well, since the subroutine really doesn't know how many parameters are on the stack, we will not have the subroutine, the called subroutine, to deallocate the arguments. But the caller always knows, because the caller is the one who set up all the arguments. So the caller is the one responsible to deallocate all the arguments, because the caller knows exactly how many arguments are on the stack. The return address is not the same, because the return address, there's always the return address. We know how big it is. There's always one. So the subroutine can deallocate that one.
Is there a way that, it's going to seem a little silly, but is there a reason why the standard doesn't, like, no, I guess not. My initial question was, why couldn't we make a stack
Mm-hmm.
using the return A, basically a stack on A, but then you have to have memory connections.
You mean using register A to store the return address?
Well, no, the reason why I was thinking that you use A as a stack.
Use A as a stack.
Yeah, never mind. This is
You mean as a stack pointer?
I get it. What I'm saying is that theoretically you could create a new stack if you were to allocate it in an empty space as A, and then you could return multiple addresses, but that's dumb. It doesn't work for various reasons.
Technically, you can do anything you want.
Yeah, so never mind. Ignore me.
Okay. Duly ignored. Okay. Okay, so now we're going to get into F. Now, before I do anything in F, because it has parameters, the first thing I usually do is to understand what is on the stack at this particular entry point. So I usually just go like using comments. I would say that there's PTR on the stack, and there's also the return address on the stack. And register D, being the stack pointer, is pointing to the return address, because the stack pointer always points to the very last thing that was pushed on the stack. Okay? Now this is really helpful because I know where to find PTR. Even though D is not pointing to PTR, it's pretty close. I know how many bytes are between where register D is pointing to and the parameter that I need to get back to. Is that okay? That distance is always a constant. It doesn't matter what the stack pointer is when I call function f. By the time I get into function f, I can always count on this picture. I don't know exactly what d is, okay, because it all depends on where function f is called within the larger program. But I always know that the register d is always pointing to the return address, and 1 byte on top of the return address is my pointer. That is the crucial part. It's relative. Everything is relative to the stack pointer. So to perform this return instruction, I have 2 things to do. Even though it looks like one single statement in C, there are 2 distinct operations that we need to be concerned with in assembly. The first one is to specify the return value. The second one is to return back to the caller. And those two are distinct operations in assembly, even though in C, it is all done by one single return statement. So now I have to specify the return value first. The return value is whatever PTR points to. So that means I need to PTR first. Okay? So the first thing some people might want to do is go like, oh, we can just increment D. So now D points to PTR. And then later on, we can decrement it back again so that it points back to the return address. That seems to make sense. Okay? But I'm going to say one more time, we cannot do it this way because of interrupts. Okay? So kind of keep this in context here when we talk about interrupts. So we cannot do something like this. Okay? We do not want to increase the stack pointer until we are ready to lose the content of whatever is below what the stack pointer is pointing to. Let me say that one more time. Really important. We do not increase the stack pointer. We do not deallocate until we are okay with losing the content of whatever is below what the stack pointer is pointing to. Yep.
Technically, though, we could go up and down the stack.
In the toy processor, yes, because I do not have the interrupt mechanism implemented. But almost every single commercially available processor has interrupts. And because of interrupts, you cannot do that. So I will explain that. Okay, I will explain why that is the case. So the way to do it is to copy the stack pointer first. So the result of this is C is now pointing to the address of the return address. The ampersand is not a typo. It is actually the case. Register C does not contain the return address. It contains the address of the return address. Is that okay? But that's not what I'm interested in, so ignore that. I'm going to increment C. Once I increment C, it becomes the address of PTR, basically my parameter. It is not PTR. It is the address of PTR. Do I want to just dereference the address of PTR? That's not what it says in the C code, does it? So I need to get to PTR first, the value of PTR. Now, when I say the value of PTR, I'm referring to the pointer itself. I'm not referring to what PTR points to. Are we clear on that one? Because I know it sounds like I'm just playing with words, but I'm not.
Can you say that one more time?
Okay, yes. At this point, C is the register C is the address of PTR, not PTR itself. What we need to get to, at least in the next thing, is PTR. So the important part is there's a distinction between the value of a pointer as opposed to the value pointed to by a pointer. The value of a pointer is really the address itself that is stored in the pointer. The value pointed to by a pointer is dereferencing the pointer to get to that location. Yep.
So we need to get the value stored at the pointer in order to get the address of that.
Yes. So that's the first thing we need to do is to do an LD instruction, which is a load instruction. There are only two instructions that can do indirect. One is store, one is load. Store will do an indirect to store something into RAM. Load will do an indirect to get something from RAM. Okay? And because of this limitation with the toy processor, it's easy to figure out what instruction you need to do when you need to do dereferencing. It's either a store or a load, but they're opposite directions. So it's pretty easy to figure out which one you actually need. So we need a load here. And it's perfectly OK to do it this way, okay? Because of the clock or the edge sensitivity of updating a register, this is OK. Because what this instruction is going to do, if you look up the microcode slides, is it's going to use register C to connect to the address port of RAM. And then it will tell RAM and say, OK, you are on, RAM cell is a 1, and we are reading RAM, which means RAM load is also going to be a 1. So the data port of RAM is going to be exporting or outputting the content of whatever location C to. And that line goes all the way back to register input of the register bank. And then the register bank would have register input select, selecting register C again, because we want to update register C. So now it seems like we have a loop of some kind, and it's always going to be unresolvable, because we are using whatever register C is pointing to update register C. So that update would never end, because the moment you change register C, it points to a different location, and then the content of that different location is going back to change register C again, and that points to another location, and so on and so forth. Well, that would be the case if the register is level sensitive. Okay? But the register is not level sensitive, is it? That was the whole discussion of D flip-flops. When we first talked about D flip-flops, it was level sensitive. The first primitive D flip-flop was level sensitive. But then when we talked about the more advanced designs, it's edge sensitive. In other words, register C is not going to update until you have that rising edge, and it will stop updating after the rising edge. So there's only one single moment in time that it will update itself. So that's what's making this instruction possible. Is that making any sense? So things that we talked about in the past, about D flip-flops, edge sensitivity, is now finally coming back and help us explain why we can use that to implement certain things that is really convenient. So after this instruction, C is now PTR itself. It is the value of the parameter. It is not the address of the parameter anymore. It is the actual value of the parameter. That is not what I want either, is it? Because in the C code, we want whatever PTR points to. I have PTR now, but I need to find out what it's pointing to. And I want that to be the return value. So I might as well just do it in A. Okay? So now A equals to whatever PTR points to, which is great. That's my return value. I'm done with setting the return value. After we set the return value, it is time to actually return to the caller. And at this time, I can do a LDB with register D, because all this time, register D never changed. Register D has always been pointing to the return address. The other way to say this is register D is the address of the return address. Okay? So if you dereference it, then B becomes the return address. Because register D is the address of the return address. By dereferencing the address of the return address, you get the return address back. And this is where we can do an increment D, because we can deallocate the return address, because we know for sure that there's one single return address here, and we know for sure that we can deallocate it because we just utilized it, or we are going to utilize it in the JMPB instruction, which will continue execution in the caller. So are we doing okay so far with this program? Yes? Okay. Shall we test it? Let's do that. Control A, Control C, and then we go back to the browser, go to my assembler. And by the way, I changed something in the assembler that might be helpful. I locked down a lot of the tabs and regions of spreadsheets that you're not supposed to change, because I saw several of you actually accidentally changing something, and then the assembler output is no longer correct. So your program doesn't do what it's supposed to, and then you look at the source code, it looks right, it should be doing this, but then your program doesn't do it. So I locked down a few things in the assembler so that should not be an issue anymore, or not as much anymore. So now we got this program in, and then we go to the RAM file tab. Go to File, Download As, CSV, and we'll call it the reference.csv. And then we go back to one instance of LogicSim. That's just the hexadecimal editor. Control R to reset the whole thing. And it doesn't look right to me, does it? Yeah, it doesn't look right. Let's close it and reopen. That's the problem with using Linux, because the operating system itself is so stable I can keep my applications running for weeks at a time because there's no need to reboot the operating system. So a lot of times the application itself would have problems, and I have to restart the app, but the operating system itself would still be stable.
Why it's the most popular server operating system.
Yep, and well, the fact that the licensing is free really helps.
Yeah, it doesn't hurt. Doesn't hurt.
Because there's no risk of whatever is licensing Linux come back to you and say, we're going to jack up the price of licensing this year. We're going to double the price of licensing, and then you go like, oh man, do we want to keep using this product or not? And usually for businesses they don't have a choice, because changing platform is very, very expensive. And there's a lot of unpredictability that goes with it too. All right, so we go back to here. We load the program back in, and it is called dref.csv. And if you feel confident, you can just run the program and then look at the output, look at the RAM content. Otherwise, you can always go to the log feature and basically just keep track of stuff that is happening on the stack. That works too. So I'm going to do both. Okay, I'm going to look at a few things in in the processor. The one thing that always keep track of the program counter. The program counter always tells you, which instruction you have executed along the path. So that's always useful. In this particular program and in all the future programs from here on, register D is also important because it is the stack pointer. The stack pointer is always important to track because we are relying on the stack to do a lot of things. Okay, and then after this, we have a pretty good idea of how much space it's going to use on stack. So what you can do is to log certain locations in RAM as well. So you basically double click on the RAM component and scroll all the way down. The earlier locations are not going to be very useful, but the later locations are. So we want to log location 255 for sure because that's my local variable X. We want to log 254. That is going to be my argument that I'm going to push on the stack. Location 253 is supposed to be the return address on the stack. So we have to log at least 3 locations on the stack. Now, if you think the program is going to take up 3 bytes on stack, you might as well log like maybe 5 locations just in case you miscalculated and something is actually using more space on stack. So I'm going to log everything from 251 all the way to 255, even though I'm fairly sure that only the last 3 locations are updated. So somebody asked, can we select all of these and then change the radix at the same time? And the answer is no. But it is open sourced, so you're more than welcome to change the source code so you can batch change the radix of components in the log. There we go. And I always like to log it to a file, okay, just in case Logisim crashes. The file, it will still be there. It's persistent. So I always want to log it to a file, and we'll call this dref.tsv, not CSV, for tab separated value. And with this all done, we can close the window and start the clocking. Control K will start clocking at full speed. And it's all done. So the first thing I'm going to do is to say, okay, I'm somewhat confident the program does work correctly. So I'm going to look into here, and it has a 7 at location 255. Is that correct? How did we initialize local variable X? 6. It was a 6. F of %x is going to return, guess what? Just 6, right? 6 plus 1 is 7. So I'm pretty sure the program does work correctly. The other thing that I'm also checking is only using 3 bytes on the stack, the last 3 locations, and I kind of mentioned that, right? 0E is supposed to be the return address. Is it really the return address? We can check that. So we can double check and go to the spreadsheet, go to the Assemble tab. Okay, so when you go to the Assemble tab, it gives you all kinds of information if you know what you're looking at. So in this case, the label is defined here. This is main return from F. Column S is the, let's see, okay, I take it back. Column V is the decimal representation. Column W is the hexadecimal representation. And of course, in this case, they're both 8. Are we seeing 8 at that location? Location 253. Let me see. Oh, 0E, that's not. Okay, did I miss something?
It's the address for the.
Oh, it's the definition, not the reference. Okay, thank you. So it's the definition over here, not the reference of the definition. So 0E is in fact correct. Okay, so I was reading the wrong line. Is that okay? So at this point, I don't feel like I need to look at the trace because everything does seem to work correctly. There's one more thing I can check, by the way. I can check register D. What is register D supposed to be at this point? 0. Okay, so let's check. So we go back to the simulator. We go to the register bank, which is a little bit to the left. And register D does have a value of 0. So everything checks out. So I'm fairly confident this program is working the way it's supposed to. Do we have any questions about this session of demonstrating how to take a C program into assembly and using parameters, local variables, and pointers? Okay, all right. So getting back to interrupts, okay, and we have enough time. I remember exactly, we are now at exactly the same time as the Monday, Wednesday class when I started to talk about interrupts, which is really coincidental. I do not plan my classes at all, as you might have noticed. Well, not in a pine needle way, okay? I only plan my classes in a forest way, not a pine needle way. Now, Professor Antos, on the other hand, can plan his lecture content down to the minute. And he can meet what he wrote down, like beginning of the class, he would say, 7:23, we'll be talking about this, and he can hit that mark. Yeah, that's amazing to me. Huh? I don't know. The one that I observed, people did ask some questions. He does not digress, though. He doesn't talk about World War II, the Yamato, the white elephant, that sort of thing. So getting back to interrupts. So we have to kind of rewind a little bit and talk about the necessity of interrupts first, because that kind of gives you the context of what it is and why it is important in this particular context. So an interrupt is a mechanism to help you with programs that have a lot of input-output devices. Okay, so I'll give you an example. So we'll go to a command line interface. I'll go to one that is bigger, like this. Okay, and obviously it's not doing anything because I'm not typing anything. So right now, what do you think this particular program, basically we call it bash, which is a shell to kind of let you type in commands and stuff like that. What do you think it's doing right now? Okay, so what we can do is I can look at the processor load. What do you think the processor load is at this point? I'm not doing a single thing. Should be pretty low, okay? So we'll take a look. It's called load average. It is pretty high. What is going on here? What is taking up all that time? OBS, okay, that's why, okay. So not counting OBS, it's not actually doing much. Okay, so this is actually good, okay? So we'll keep OBS in mind in this case. Okay, but when you look at this particular program, which is the command line interface, it really should not be doing anything because I'm not typing, right? But if you are to write a program to interact with an end user so that when the end user types something, you would process it, how would you do that?
Wait until all input is given and then.
Okay, but how do you wait? That's the biggest question is how do you? Because let's assume that there's no operating system underneath. Okay, so you're interacting directly with your USB controller, which hooks up to the keyboard and your mouse and stuff like that. Yes. That would be a smarter way to do it.
Just
Hmm.
certain like amount of inputs come in. There's this threshold of time before the window closes for any more additional.
Okay, so having setting up a time, and say, okay, I'm waiting, let's say 20 milliseconds, and then we check again. Okay, so that's smart. But you'll be using polling. Okay, yep.
I mean, isn't like the best way to do it would be to just like do a while loop forever, always check for input.
Yep.
But then you hate your system. That's yeah. But I mean,
But that's the way they did things in the DOS and CPM days, because back in those days, the operating system itself cannot handle multiple programs running at the same time. So if your operating system cannot do it, you might as well just say, keyboard controller, do you have anything for me? And then right away you ask the question again, keyboard controller, do you have something for me? And then right away you ask the question again. Yep.
You wait for a particular input.
Yes, the program is really waiting for a key code, because every time you press something, every time you press a key and every time you release a key, there's an event that is reported back to the keyboard controller as a key code. So there's a key code for pressing a key, and there's a separate key code for the pressing or releasing a key. Excuse me. And that's how auto repeat works. Is your operating system is actually figuring out that you have pressed down a key for a certain amount of time, and then it will just do the auto repeat. But the idea is, without the concept of interrupts, you'll be doing polling. You'll be asking the keyboard controller again and again and again, do you have something? Do you have something? Do you have something? Do you have something? So that is really bad in this context, because if the command line interface is using that approach, I would have no processing resources left for OBS. We wouldn't be streaming. We wouldn't be encoding the video and the audio and streaming to YouTube at the same time, because the command line interface itself is consuming every single bit of resource just to check, did I type something on the keyboard? Did I press a key? Is that okay? So it's not an effective use of processing resources. So that's interrupts. So if you think about my office hour or lab time, okay, and let's say I'm the processor, and you peripheral I/O devices, okay. Polling would basically be me walking to each one of you in a circle, round robin, and say, do you have a question? Okay. Do you have a question? Okay. Do you have a question? So I will do that like 26 times and then go back to the first person and do it all over again. I don't do that in the lab. I would doze off. I'll check my phone. I'll do some texting. I'll do some web browsing, right? Until one of you raise your hand and go like, or come to me because I'm too absorbed, with my own stuff, and you tap my shoulder and go like, Tag, we got a question. Can you come over and take a look? That is an interrupt, okay? Because you're interrupting what I'm doing in order to, quote unquote, surface an interrupt, okay? So the source of an interrupt is usually an I/O device having a byte available for the operating system to process, or it has room to transmit one more byte or one more packet. So it's asking for the operating system and go like, hey, we got space now. Do you have something else to transmit? Yes?
Is that done on the hardware?
Yes, it is done on a hardware level. It has to be supported by hardware. So the processor itself has to have the interrupt capability built into it in order to have interrupts.
What would that look like? Like where?
Okay, so.
On a high, I don't necessarily want you to have to add interrupts to your processor, but like where would it be added?
I can at least illustrate it in the source code fashion. Okay, so let me go back to the tab. Okay, I cannot figure out which one is which one, so I'm gonna have to scan. Okay, there we go. Okay, so basically between any two instructions, the execution of this instruction and the execution of this instruction, the processor has a mechanism to say, does any hardware device require my attention? So there's a particular line, an actual physical pin on the processor, at least one pin, I should say, at least one pin on the processor that is called the interrupt pin. So if the interrupt pin is not asserted, then the processor goes, I'll just go to the next instruction, no problem.
So it simply does a check in between each one.
Yes, it will do a check between instructions, between the execution of opcodes.
And then how, if there's multiple pins,
It prioritizes.
does it query all of them?
Yes. But it's all done in hardware, so it's not sequentially checked.
Oh, it's done
It is
all-
done all at
right,
once.
Yes, okay, that makes sense.
Yeah, and it doesn't use any execution time of your instruction either, because that's all done in parallel using hardware gates. It's combinatorial gates that is doing that. Okay, so between the instructions, the processor will check those pins and see if any hardware device requires its attention. Yep.
I was just gonna ask, so like the instruction itself generates the interrupt, and then is there just like some address stored somewhere else for like handling it?
Right, so that is the next thing, okay? So it's not the instruction that is generating the interrupt, it is the hardware device that requires the attention that is generating, quote unquote, generating the interrupt. So let me be more specific. When we say generate the interrupt, it's really just the hardware device asserting the interrupt line to indicate that it needs attention. Is that okay? So let's say the keyboard controller says, okay, somebody just pressed the key, there's something to process, okay? So then the processor will check that pin and go like, oh, okay, the keyboard controller has something for me. Yep.
Sorry, I'll let you go a little bit farther.
Oh, okay.
It's a bit deeper.
Yep. But what is the processor going to do? The processor itself doesn't know what to do with the keyboard controller or what to do with that key press, okay? Because the processor doesn't even know whether you have a QWERTY keyboard or some kind of international keyboard or some different layout. It doesn't know what the key code is corresponding to in terms of the actual character, okay? So it is the operating system. It's some other code that you are going to have to write to interpret the key code and go like, oh, that's the lowercase key because the caps lock is off, la 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 la, okay? So it is actual code that has to execute when an interrupt is raised. Go ahead and then you. Yep.
So you mentioned that there are processors with multiple pins.
Yes.
Those pins generally indicate the priority, right?
Yes.
So if there's a lower priority than what it is currently doing, is there a queue system?
There's no queue per se. Whatever.
Just wait for the next.
It just waits, exactly. So if you are a low priority device, let's say you're the keyboard controller, and there's another, let's say it's the DMA, or direct memory access controller, which handles massive amount of data transfers, and that's why it has a higher priority. So if the processor is busy surfacing the DMA controller and has no time yet to process your request, you just keep asserting that line. You just keep holding on to that line and go like, I still need attention.
Is there any instance where a processor would have a queue system of any kind?
No, because it is implemented in hardware. So all the pins are coming in parallel. So they're all independent, and each one is controlled by the input-output device that it attaches to. So there's no actual quote-unquote queue. In other words, you don't put yourself into a queue and then the processor dequeues.
So then what is a cache? Because like modern processors I know have a certain amount of cache.
Yes. Cache only has to do with memory access. It has nothing to do with interrupts.
Okay, so it's just like an intermediary between accessing the RAM.
Right. So that you don't have to go all the way to the actual, yep, much faster because it's on chip instead of off chip. Yep.
So you said that the interrupt is connected to all these inputs. Does that mean there's like thousands upon thousands of wires connecting to this single?
No, there are only so many IRQ lines. Okay, so if you want to look up, how many interrupt lines there are, in the case of the x86 architecture, the conventional name is IRQ. I think there are maybe like 1632 of those.
So like there are wires though, physical circuitry that has to connect to this interrupt, essentially.
Yes, they are actual physical pins on the processor connected to.
Still quite a bit of wiring.
Yes, but you can multiplex. See, the other thing is you can use software to multiplex and have multiple devices connected to the same single interrupt pin, and then the processor, once it knows that one of these devices is requesting, it can then query and say, okay, which one of you required attention? Yes?
I thought x86 had like an actual interrupt instruction. Is that just like an operating system kind of thing?
Okay, that's a much more advanced topic than what we are getting into. So we'll do that. Okay, so can you push that on the stack so that we can get back to that later? That's what the stack is good for, right? I cannot do it just yet. Push it on the stack. So by the time we current items will eventually pop to that single item, right? Okay. So the key question now is, let's say between these two instructions, okay, I don't really care which two. Let's say between these two instructions, after the increment and before the load instruction, the processor notices, oh, the keyboard controller needs attention because that line is now asserted. So what it needs to do now is to say, I'm done with the increment instruction, but guess what? Right now, I am going to what we call an interrupt surface routine, or in short, it's an ISR. Okay, so an interrupt surface routine looks just like any subroutine. Okay, it's just code that you're going to write. You use the same kind of mnemonics. You use the same kind of code. It can be in the same program. So it will go to that particular ISR. It contains the code to talk to the keyboard controller. It's like, okay, what key code is reported? Okay, cool. Okay, now you're free to go. Okay, or if you want to turn on one of the LEDs, like the caps lock or the num lock, LED, you can also instruct the keyboard controller to turn on those LEDs. So when you're done, so you're basically diverting your execution path from this increment, or excuse me, from the load instruction to somewhere else. When the ISR, the interrupt surface routine, is done, what do you think it needs to do? It needs to get back here. Is that okay? So the concept of interrupts from the software perspective is it's almost as if a hardware device is calling a subroutine in your program. Yep?
So like that context switch, when the interrupt handler or interrupt service routine is running, like they're going to be using all of that space on the stack, like above or
Below.
The deallocated stuff, like all of that
Yes.
could potentially change.
Exactly, because it is also like calling a subroutine. So the interrupt surface mechanism, which has to be a part of the processor, will push the address of the load instruction on the stack, and then it will proceed to the corresponding location of the ISR, execute it. At the end of the ISR, there's a return, quote unquote, return statement, just like what we do to return. And it's going to return back to the load instruction because we got interrupted between the increment and the load instruction. So it has to get back to the load instruction. But the problem is it has to save that memory location on the stack. And depending on your architecture, it can be the same stack that you are using. So that means if you increment the stack pointer, you do increment D, and then the interrupt happens, the interrupt can immediately use the location that you just freed up. Is that okay? So that means at any time in your code, you have to be sure that you do not need the content of any location below what the stack pointer is pointing to, because between any two instructions, an interrupt can happen, and it can use whatever is below what you see your stack pointer as. Yep?
You also use the values that are in the registers that we see.
Yes, so the ISR has to be very careful to preserve the values of all the registers, including the flag register, which the toy processor has no capability of. So the toy processor is lacking a few important features to handle interrupts.
Would it put those all on the stack after D?
Yes. So typically what happens in ISR is the first thing it does, the saving of the return address is done without actual instructions, but the first thing your ISR is going to do is to push all the registers on the stack. Then it can do whatever it needs, right? At the very end of the ISR, it pops all the registers. In other words, it restores the value of all the registers. In this case, it has to restore registers A, B, C, D, and, well, not D, because the stack pointer is automatically restored. So registers A, B, C, and also the flag register before executing the return statement to get back to the actual code that really should be executing, not counting the interrupt. So that is the reason why you always want to decrement before you use a location. You always decrement the stack pointer, and then you use the location. that is pointed to by the stack pointer. Because the agreement between the stack pointer, between any code and the ISR is whatever is below what the stack pointer points to is available. You can change that. So is that kind of helping you understand why we have to do things in a specific order? Cool. Yep. Mm-hmm.
Say you went so far that you went all the way to your RAM code that was in the instruction.
Well, then there's no saving you because because then you'll be overwriting your own code, and it does happen. Okay, something like that does happen. Depending on the architecture, the early architectures do not have any type of protection mechanism. So when you're looking at the early computers, so on the PC side, they make use of the 8088 processor, which has no protection mechanism. And then on the Apple II side, they use the 6502 processor, which also does not have any type of protection mechanism. So we do have programs that will occasionally overwrite, actual instructions because the stack has gone down far enough to overwrite instructions. And that's a pretty nasty problem to have. So are there any questions regarding the use of the stack or the stack pointer? No questions? There's no question about whether your program that you write in your other classes should worry about a stack being used by interrupts? What do you think happens? So let's say you're running Windows 10 or Linux or Mac OS 10, okay, and you're in the debugger, okay, you look at the stack pointer and you look at the instructions or the locations below what the stack pointer is pointing to, and you will come back to me and say, Tech, you lied. Why? Because the content of the locations below what the stack pointer points to never changes. And I keep typing on the keyboard, and in the background, OBS is running, the network is going, la 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 la. How come the stack doesn't change? So what do you think?
I was just thinking that whenever the interrupt service routine runs, it pushes everything that's in registers and stuff like that onto the stack, and when it's
Yeah.
out, it just pops it back.
Yeah, but then you should be able to observe, the content below what your stack pointer is pointing to should be changing all the time because interrupt is happening in the background all the time. But you won't be able to observe that. The reason is because modern processors have protection mechanisms, for one thing, and two, they're multi-threaded. Your operating system is multi-threaded. The definition of a thread is each thread has its own stack. So when you have multi-threading, you basically have multiple threads. When you have multi-threading, you basically have multiple stacks. The kernel has its own stacks. And whenever you have an interrupt happening, it's using the stack of the kernel, not the stack of user space. And that is why you will never see anything changing on your stack in user space. So the kernel stack is doing all of this stuff, okay? Interrupt is going to use it, but your user space stack is going to be like, there's nothing happening to it. Yep?
Can they combine themselves, like the threads combine their stacks together to almost like a two-dimensional stack?
No, because the stacks do, the allocation of stacks is kind of dynamic. So if you have a process is a program in execution, and the process can contain multiple threads. The moment you start a thread, the code that is started is responsible to allocate the space that will be used as the stack space for that new thread. But that allocation can be done by statically. You can basically say, here's an array as a global variable. Use that as the stack of this particular thread. It can also be dynamically allocated. In C++, you can say, I want to use new to allocate a block and then use this block as the stack of this particular new thread. You can do it that way. So there's no specific way to allocate for a new stack. So it's not a two-dimensional which basically lock down the stack. prior to the allocation of the entire thing. Okay, so one more thing, because you asked a question, what is the interrupt instruction? Okay, so with interrupts, it is more or less a hardware thing. Okay, your keyboard controller wants to assert an interrupt line saying, I need surface. Your hard drive controller says, I need surface. Your DMA controller says, I need surface, and so on and so forth. An interrupt instruction is your software program, your program itself, triggering exactly the same mechanism to go to a particular place to execute code. And then you would ask, but why would we want to do that? We can just call and then use return. Why do we want to go through this hardware mechanism to do it? It has got two things. I don't have enough time to explain each one. The first thing has to do with privilege escalation. In other words, in user space, your instructions can only do so much. The moment you try to convince the hard drive controller to erase the hard drive, your operating system is going to slap your little hand and say, nope, not going to do that. Okay? Give it a try. Okay? See if you can convince your operating system to wipe the drive in user space. You cannot. You cannot execute instructions like that because it is protected. Okay? So now the question is, since your program has no direct access to the hard drive or the video control, display controller and stuff like that, how do you actually store something on your hard drive? Well, you have to convince the operating system to do it, right? So how do you convince the operating system and say, I need to store these 2048 bytes, onto that location of the hard drive? Okay, so you think about the alternatives, right? One way is just a call, okay? I know which subroutine to call, I'm just gonna call that subroutine. But if calling the subroutine can get the job done, that means you are already running at the privileged mode where you have access to the hard drive controller, which means there's no protection mechanism whatsoever. But if you think about the interrupt surface routine, do you think the ISR needs access to the hardware directly? Do you think the ISR of your hard drive controller needs to access the hard drive registers? Obviously, yes. So the hardware interrupt mechanism has an automatic mechanism to increase privilege level to what is needed to surface the interrupt. And when it returns from the ISR, it will return the privilege level back to what it was. In other words, it's automatic. When you surface an interrupt, the ISR is automatically running in a high privilege level. And then when it returns back to your code, it is automatically returned to the user level privilege level. Is that okay? That is how you use the software interrupt instruction to ask the operating system to do something. Because by executing the interrupt instruction, it is going through exactly the same motion as surfacing an interrupt. By increasing the privilege level, execute code at a certain location, which in this case corresponds to your operating system somewhere. And then when the operating system is done with whatever it needs to be done, when the operating system returns to you, the privilege level will be lowered back to the user level, so everything is safe again. That is the reason why we have the software interrupt instructions. Kind of given 5 minutes, that's how I can explain it.
Like most system calls should be using that kind of thing?
Yes. And in all modern operating systems that I know of, they all request operating system services through a software interrupt instruction. Now, which one kind of depends on which operating system and which architecture, but they always use a software interrupt instruction to do it. All right, well, we are running out of time, so I'm going to stop the lecture at this point. And then the late lab people